Hello, my name is Matheus de Oliveira, and today I'll be presenting the paper entitled Learning-Based End-to-End Video Compression Using Predictive Coding. This work here was developed by teams from University of Brasilia and Samsung R&D Institute, Brazil. So in order to introduce the topic of video coding, I'm going to give a brief description on how traditional video codecs work. So, given a video sequence, which is a frame sequence, we can choose from two major approaches to encode these frames. So the first approach is the intra-frame coding, which only the spatial redundancy is explored. So this frame is directly submitted into a transformation, followed by a quantization, and these coefficients are submitted to an entropy codec. The second approach uses information from previously reconstructed frames, which are available to both encoder and decoder. So from these reconstructed frames, we can make some motion estimation, which are used to predict the current frame that we are encoding. Then we need only to encode and send to decoder the difference between our prediction and the real frame. After we obtain this residual here, it's usually also encoded following the same steps used by the intra-frame coding, which are transformation, quantization, and entropy codec. So after this quick introduction on video coding, we can now introduce the neural coding domain. So the reference work here, the first reference work, was proposed by Valet et al. And here the authors propose an image codec which consists of a variation autoencoder. So we can see some schematic here. In the proposed paper, both the encoder and the decoder have 3 convolutional layers, and the cost function have a format like this one here. So this loss, we can see that is a weighting between the average rate per image and a distortion metric between the input image xy and the output image fy. So this hyperparameter lambda here is associated with a model operating point. So if we would like to obtain a model that prioritize more rate or distortion, we should change this value of lambda and retrain a new model for that. By retaking the autoencoder's schematic, we see that the output of the encoder was called y. This y tensor here is also denoted by latent. In this paper, the authors have proposed that all dimensions of this latent follow standard normal distribution. So from this model, they can further compress this tensor with already reduced dimension compared to the image. So the next benchmark paper is actually a continuation of the proposal presented earlier. So Meaning et al. Have proposed that instead of using fixed parameters for the Gaussian distribution of the latent dimensions, we should learn these parameters for each of the dimensions. This goal was achieved by introducing an auxiliary autoencoder. So the latent y is the input for this auxiliary autoencoder, and the output is our mean and variance for each of the dimensions of this main latent y here. So it's worth noting that the probability model adopted for the auxiliary autoencoder is the one with fixed parameters, and also that despite the change in the probability model of the main latent, this new image codec here has adopted the same loss function as the previous one. So after conducting this short contextualization, we can start to discuss our proposed video codec. So at first we can talk how our codec deals with the frame sequence. So our codec splits actually the frame sequence into independent group of pictures as shown here. So you have the frame sequence and the independent GOPs. The GOP structure is always the same. The first frame is an interframe and all the others are interframes. Interframes are also referred to as p-frames. In our codec, every p-frame uses only its immediately preceding frame as reference. In most modern video codecs, there are much more complex structures for selecting the reference frames and for making this prediction. So this kind of approach can be incorporated into our proposed video codec in the future. So after presenting our GOP structure proposal, the next step is to explain how interframe coding is performed. So as commented earlier, the coding process of an interframe is analogous to the compression of an image. So we can choose one of the reference models, one of the reference variation autoencoders to do this task. By retaking our GOP structure, we see that only the first frame is an interframe. Therefore, we can choose the computationally cheapest version of this variation autoencoder to perform these interframe coding. As we can see here in the image, the interframe coding was submitted to the non-parametric variation autoencoder. The non-parametric is the version with a probability model with fixed Gaussian parameters for the latent distributions, which is since it has only one autoencoder, it's the one that requires less memory and less computational power. So after having this first interframe reconstructed, now both encoder and decoder can deal with p-frames, since now they have the first reference frame here. In order to have various operating points for our video codec, this architecture here used for interframe coding was trained with 3 lambda values. That is, we have 3 operating points for our interframe coding. So the last stage of our proposed video codec is in interframe coding. The reference variation autoencoder was also used here, but some minor changes were done and some blocks were added. The first remarkable point here is that instead of using only the target frame as input to the model, we concatenate in channel dimension the reference frame and the target frame. Therefore, the input of the variation autoencoder has now 6 channels. Here you can see that we use the parametric variation autoencoder. It's the one with the auxiliary autoencoder for predictive parameters for the latent distributions. The second important difference here is that the output of the variation autoencoder now is the input for 2 other networks. The first network is the motion estimation network. This network here has the goal to produce parameters for a warping transformation that will be applied in the reference frame. Remember that this reference frame is already available in the decoder, so there is no issue in this operation. The second network is the residue network, which aims to find an estimate for the residual, which is the difference between the target frame, which is the p frame we want to encode, and its prediction. Since we have a prediction for our target frame, which is the output of our motion estimation network, with the warping operation applied over our reference frame, and we also have a residual estimate, we can sum these 2 tensors and obtain our interframe prediction. It's important also to highlight that both these two networks here have two convolutional layers. Despite the architecture changes here, the original loss was maintained. And from this loss, also with the goal to produce various operating points for our video codec, we trained this whole architecture here for 5 different values of lambda. After explaining how videos are divided into a GOPS structure and how intra and inter codecs work, we now can have a overall visualization of our proposed video codec. Here in the figure, you can see the 3 versions of our intra codec and the 5 versions of our inter codec. Now we can have 15 combinations for these different operating points. Assuming that the higher the version number, the higher the lambda value associated, this model here, for example, will consume more bits, but will generate reconstructions with higher quality. So seeing this example, this intracodec here will generate reference interframes with high quality, while this intercodec here will encode p frames in our operating point with emphasis on saving rate. Because intra and inter codecs are trained separately, different datasets had to be created in order to perform this training stage. So the intra codecs were trained by a dataset created by our team. This dataset has almost 90,000 patches that were extracted from 6 different datasets. The pre-frame codecs were trained from pairs taken from 275 videos that were extracted from the UGC dataset. In the evaluation stage, we used 5 videos from the GVET dataset, and both stages, the training and test stages, were performed on videos and images in the YUV color map. Here I present the results obtained by the first version of our proposed video codec. For both videos here, we see that the rate distortion curve obtained by our proposed codec in green is in a region close to the curves obtained by the all intra modes of the most recent traditional video codecs, HEVC and VVC. We also note here that this closeness is more observed for the subjective metric MS-SSIM. As a second part of the results section, I propose here some visual comparison between frames that were generated by different codecs. Here at first, I show some comparison between frames that were obtained from all intra versions. Actually, these frames here are essentially a result of our reference work. However, here I propose some comparison between frames, between p frames actually. Although our codec uses far more bits than the low delay p VVC, this visual comparison here allows us to realize that end-to-end learned codecs indeed can be used for the task of video coding. Finally, I would like to say that I and all the other authors are at your disposal to exchange ideas about the subject. I leave here my email for contact. I greatly appreciate everyone's attention and have a nice conference.